Welcome to video 7.1b, thermal expansion and gas laws. Remember, we ended our last video talking about how thermometers work and the fact that liquids and most substances tend to expand as they get hot and contract as they get cold is why thermometers work. We're going to focus on that aspect of thermodynamics in this video. So let's start with thermal expansion of solids. We know from experience, although we may not have thought about it yet, that when things get colder, they shrink. When things get hotter, they expand. This is true whether we're talking about solids, liquids, or gases. There is the exception of water, but we'll get to that in a little bit. If we talk about solids in particular, and we have just a regular bar sitting there, and this bar is at some temperature that we'll call T0 for original temperature. At this point, it is a particular length, which again, because it's its original length, we will call it L0. When we have a bar that it has a particular length of L0 at temperature T0, and we heat it up, then according to what we have seen in life, and according to the idea that when we increase a temperature, we're increasing the average kinetic energy of an object, things that have higher kinetic energies tend to move more, not just faster, but more as well, and they therefore expand. In doing these observations and in recording what was seen, it has been proven that when you change the temperature of an object, its length will change proportionally. And this is true whether you're increasing the temperature or decreasing the temperature. Not only is the change in length proportional to the change in temperature, but the change in length is also dependent upon and proportional to the original length of the object. So your change in length is proportional to two different things here: the amount you change your temperature and what the original length of the object was. So if I change my temperature of the rod that I have drawn here to some other temperature, which I'll just call T, then the length of that rod is going to increase in amount delta L, so that the final length of the rod is simply L. And this increase in length here is going to be proportional to how much our temperature changed, as I said before, and to the initial length of the rod. We put these two proportionalities together and we can create an equation with them as long as we put in a proportionality constant. And so our equation for linear expansion of solids becomes delta L is equal to alpha L0 delta T. So delta L is our change in length. Alpha is the coefficient of linear expansion. Now the coefficient of linear expansion is dependent on what material you're talking about. However, it also does change slightly depending on what your temperature range is. We're going to be using only situations where our change in temperature does not affect the value of the coefficient of linear expansion. So we'll get to a table of these in just a minute. So it's alpha, which is our coefficient of linear expansion, times our original length, times our change in temperature. As is true in any unit that we do in physics, we need to make sure that we are talking about units along with our measurements, because if you don't have your units correct, then your answers are not going to come out to be correct. So in linear expansion of solids, we need our units to be the following. We need our length to be in meters. Our coefficient of linear expansion is in degrees Celsius to the -1, which we can also write as 1 over degrees Celsius. Our original length also needs to be in meters, and our change in temperature needs to be in degrees Celsius. So you can see that as we go through, we have a 1 over degrees Celsius times a degree Celsius. Those units will cancel, and we end up with meters equaling meters. which is what we want. So again, if we're talking about how much does an object expand, a solid expand due to a change in temperature, we need to look at this equation right here. Delta L equals alpha L naught delta T. Make sure you have this written down. Not only will you need it in the problems solving in class, but also you can have it on your note card for the test. Let's take a look at the table of coefficient of linear expansion values. It is table 13.1 from your textbook, so you can find it. It lists a number of solids and their coefficient of linear expansions in the center, and then the volume expansions on the right in the right column. Notice that these are coefficients near 20 degrees Celsius. And we can see that they're all written in the scientific notation, although some of them not proper scientific notation, so that they're all to the power of -6. So if we take a look at some common ones, for example, iron or steel is 12 times 10 to the -6, whereas lead is 29 times 10 to the -6, and glass is, Pyrex glass, is 3 times 10 to the -26. Sorry, -6. What this means is that lead is going to expand significantly more than glass over the same temperature difference. And those are things that we want to keep in mind, because those are some of the questions that in reality are very important depending on what it is you're making and what you're using this for. We'll come back to the volume coefficients in just a minute. But let's take a look at an example that involves our steel here. We have a steel bridge. It is 200 meters long at 20 degrees Celsius. If the environment the bridge is in can change temperatures from -30 degrees Celsius to +40 degrees Celsius, how much could it expand and contract? So this is quite a large temperature range, and we have steel, so we want to see how much do we have to keep in mind, how much leeway do we need to leave for when we construct this bridge to make sure it doesn't fall apart on us. The easiest way to approach these problems is to write down what you know, write down what you're looking for, and then write down the equation that you can use. So I know that the original length of my bridge is 200 meters. I know that the original temperature of my bridge is 20 degrees Celsius. I know that it's made of steel, so I can go back to the other chart on the last page and we can look for alpha. And I recall having just said that it was 12 times 10 to the -6, 1 over degrees Celsius. So those are all of the things that I know. Now that's not all that I know. Now there's two more things that I know. I know that one of my T finals is -30 degrees Celsius, and my other T final is a +40 degrees Celsius. What I want to know is how much could it expand and contract. So really, I want to know if my final temperature is -30, what is my delta L? And if my final temperature is +40, what is my delta L? So you need to solve next thing you need to know is write down your equation. The equation that we just talked about on the other page was that delta L is equal to alpha L naught delta T. Remember, the deltas mean change in, so this will give us the change in length. So we have to find out alpha, L naught, and delta T in order to be able to solve this. So if we take a look first, let's do the top one when it goes to -30. Delta L is equal to alpha, 12 times 10 to the -6, times L naught, which is 200, times delta T. To get my delta T, I'm going to say I start at 20 degrees and I go down to -30. So my difference is going to be a +50. My delta L for my contraction, then, if I do that math out, is going to be a -12 times 10 to the -2, or 12 centimeters. So my 200 meter bridge is going to contract 12 centimeters. If it gets down to as cold as it can go. So contract, it's going to get shorter. So you got to make sure you have allowances. You have at least 12 centimeters at each end holding up the bridge. Now let's do the other way. Let's find out what happens if it gets really, really hot. We still have our alpha of 12 times 10 to the -6 We still have our original length of 200, but now our delta t is going to be 40 minus 20. Okay, so I noticed, I'm sure you've noticed that up here I actually put 20 minus the negative 30. Sorry, it should have been 30 minus 20. Negative 30 minus 20, not the other way around. I apologize. And when we do this, we come up with a change in length for our bridge when it's expanding to be 4.8 times 10 to the negative 20. No, it doesn't. 4 times 8 times 10 to the negative 2 meters, or 4.8 centimeters. So again, in the first case, the bridge was going to contract 12 centimeters. In the second case, it was going to expand 4.8 centimeters. The reason that they're so different is because our contraction is over a larger temperature change than our expansion. The rates at which they expand and contract are the same, but our temperature differences are significantly different here. On the expansion, you only have a delta T of 20, whereas on the contraction, you have a delta T of 50. So what does this mean? Well, this means that when you are building a bridge, designing your steel bridge and designing the supports, you've got to make sure that there is some way for the bridge's length to get smaller by 12 centimeters and get larger by 4.8 centimeters and not break the bridge. The way that you do this typically is with a joist, like that. So an expansion joint, where in this space here, you can see that if the bridge was going to expand our 4.8 centimeters, then that would be how far this distance needs to be. If it gets all the way there when it's the largest, and the other part of it is you have to make sure that this section that is still overlapping is larger than your 12 centimeters that you need for contracting so that it can make it all the way in there. So if solid things like bridges expand, then we also have to think about the fact that solids can be in any shape and they too can expand in a linear direction. If we think about a ring, and we have a ring of metal, or even a ring that goes around your finger, we have a ring of a certain thickness, and assume this is the same thickness all the way around. If we have this ring at 20 degrees Celsius, then, and let's say that its center hole here is 5.0 centimeters. If we place this ring into a fire, we just said things expand when they get hot, so things should expand. The question becomes, does the hole in the center of this ring get smaller or get larger? And we'll talk about this more in class, but I really want you to think about this. And of course, you're going to have to be able to justify your answer. Let's say that this ring is made of gold. Okay. Does the diameter of the inside hole increase or decrease as the temperature increases? I have a couple of other questions along those lines as well that we'll talk about in class, but you can also think about them. How do you use temperature and the fact that things expand when they get heated to open the lid of a jar that is stuck? As you saw on the table a couple of pages back, when things expand, they don't just expand in one dimension. They also expand throughout their entire volume. So if we take a look at what happens with volume, we end up with something very similar to what happened with linear expansion. Linear expansion, we really only talk about it in terms of solids. Unless you're doing something like a thermometer, then you can use linear expansion. You can think about it in terms of linear expansion as long as the thin tube that you are using for your thermometer is a consistent thickness the entire way. But for volume expansion, we can talk about volume expansion with solids, liquids, and gases. It doesn't matter. Gases are a little bit different, so we'll talk about them in more detail at the end. But the equation for volume expansion is very similar to the equation for linear expansion, where your change in volume is equal to your coefficient of volume expansion which is beta, times your initial volume, times your change in temperature. Beta has the same units as alpha does. It just is for volumetric expansion instead of linear expansion. So again, your change in volume has a unit of cubic meters. Beta has units of 1/degrees Celsius. Your original volume has units of cubic meters. And your temperature still has units of degrees Celsius. So because things expand in the volume form, and if we look back for a second here at the list, we look at the coefficients of volume expansion, they're significantly larger than those of linear expansion, which makes sense because volumetric expansion for solids is essentially just linear expansion in 3 dimensions. Now notice we also have some for liquids and then some for gases. In particular, this gas is just air, the ones that's listed. Notice that those coefficient of volume expansions are huge, significantly more than with solids. So when we're talking about things expanding volumetrically, we have to keep in mind that they expand in all dimensions, not just in one, and that the result is going to have a greater effect than just linear expansion, which is why you don't want to top off your gas tank if you are filling your gas tank in your car. Because as you're sitting there at the gas station and you're filling up your tank, the gas that's coming in is at an ambient temperature of the ground. And then when the gas, so it's a liquid form, when the gas gets into your tank is going to be warmer, and then the liquid inside, the gasoline, is going to expand. And as it expands, your tank isn't going to expand with it because your tank's not having a temperature change. Only that gasoline is. So that gas is going to end up overflowing and coming out of your tank. So this is especially true when you are filling up in the hot weather. Do not top off your gas tank when you're filling it, or you will spill gasoline, and that's not good for the environment. Now, the one thing that is unique about the whole idea of volume expansion, and the one thing that does not obey these laws all the time, or this rule all the time, is water. When water approaches 4 degrees Celsius from temperatures higher, so let's say that we are at 100 degrees Celsius, we go down to 4 degrees Celsius, and it will in fact contract. However, between 4 degrees Celsius and 0 degrees Celsius, when it becomes ice, it expands. So from 4 degrees to 0 degrees, our water is expanding. If it's expanding, that means that it's becoming less dense. So the 4 degree temperature water is going to be the most dense water that we have. Cooler than that, it's going to be less dense. And at 0 degrees Celsius, of course, we know we get ice. And ice is even less dense than water is. If you continue to decrease the temperature of ice, it will start to contract, but right around 0, from 4 to around 0, liquid water and solid water are expanding. This is actually super important to not only remember, but to understand the consequences of. If we look at a lake, for example, okay, here's my fabulous lake. And during the summertime, of course, we've got water in it. We've got some nice little fishies, and they're all happy. But as the temperature starts to drop and it gets colder and colder and it gets closer to 4 degrees Celsius, the water temperature drops, and the 4 degrees Celsius water, because it's the densest, sinks to the bottom. The cooler water is going to be up top here, and that's going to result in ice forming. This is why ice forms on the top of lakes, because water at 0 degrees Celsius is less dense than water at 4 degrees Celsius. So the 4 degrees Celsius water sinks, and the 0 degree water goes back to the top, and the ice is formed at the top. If this did not occur, if ice did not float, and if water did not expand after 4 degrees Celsius, then we would have no life on Earth in water over the winter time. It would not have survived because it would have frozen from the bottom up. But because there's always that inversion of warmer water down to the bottom, ice does not form at the bottom. So for volume expansion, remember this equation with the units underneath it. Please make sure you use the variables for the equation and keeping the units in mind and making sure your values are in the units as well. Now, gases have their own set of rules. There are 3 particular laws that go along with the gas laws. They're called the gas laws, and they were found by scientists named Boyle, Charles, and Gay-Lussac. And their laws explain how ideal gases expand and contract under different circumstances. An ideal gas is essentially what we're going to assume all gases are. So we'll come back to what that means in definition in class time. But for the most part, when you take a gas, think about a balloon for a moment now, and you try to compress it, you have some issues going on there because there's pressure inside the balloon pushing outwards. Keeping in mind that gases fill all of the space they have. If you then try to compress their space, there's going to be a change in the pressure. For the moment, I am just going to tell you what these laws are. You're going to be investigating them in more detail in our lab, which I'll introduce in class Tuesday. First of all, one of the things that Boyle, Charles, and Gay-Lussac have in common with all of their labs is that in order for us not to have to worry about negative values, we only use temperature in Kelvin, okay? Because at 0, we've never reached it. You can't get anything colder than that. Also, keep in mind that a change of 1 degree Celsius is also a change of 1 degree Kelvin. So if you're looking at changes of temperature, then it doesn't matter. You don't really have to convert between the two. But if you're looking at a particular temperature, you have to have them in Kelvin. What they all found was that there is a relationship between pressure, volume, and temperature of gases when you allow them to expand or compress, depending on what the situation is. Their overall ideal gas law is one that you will come up with a version of in the lab. But to begin with, let's look at the 3 different relationships that they found. There are 3 variables: pressure, volume, and temperature. And what they were looking at is what happens if you change one of them. If you change the pressure, what happens to the volume if you keep the temperature the same? If you change the volume, what happens to the pressure if you keep the temperature the same? If you change the volume but keep the pressure the same, what happens to the temperature? Etc., etc. And what they determined was the following. If you keep temperature constant, then you start out with a gas at pressure 1, volume 1. When you are done expanding or contracting it, as long as you keep the temperature constant, then that will equal the product of the pressure volume at the end. So P1V1 equals P2V2. So this is an inverse relationship between volumes and pressures. Another relationship that they determined was between volumes and temperatures. The ratio of the volume to temperature at the beginning of your compression or expansion is equal to the ratio of the final volume and temperature of your gas after compression or expansion, assuming pressure is kept constant. And then finally, the third relationship that they looked at, and they did this individually, but based on what was going on in the work with each other as well, but they each look at a different relationship. Finally, the third relationship was that the ratio of pressure to temperature is the same relationship as volume to temperature. So P1 over T1 equals P2 over T2. V1 over T1 equals V2 over T2. P1 V1 equals P2 V2. You combine these together, and typically this is how you see them. P1 V1 over T1 is equal to P2 V2 over T2. So the initial pressure times volume divided by temperature is equal to the final pressure times volume over temperature. There, like I said, there is one more relationship that comes out of this, which is called the ideal gas law, which you'll come up with in the lab. But basically what this is saying is that if I know two of the conditions, whether it be the pressure and temperature, volume and temperature, or pressure and volume, I can figure out what they were at the end as well. If I want to keep temperature constant, then the T1 and T2 are the same, so they cancel out. If I want, and I get the first equation. If I want to keep pressure constant, then P1 and P2 are the same, and mathematically they cancel out. So then I get V1 over T1 equals V2 over T2. And if I keep volume the same, they cancel out, so P1 over T1 equals P2 over T2. So this equation here in the center is typically the one that I focus on to use when I'm talking about the gas laws and trying to figure out what's happening with gases when they are compressed or expanded. So at this point, you have three equations now. You have delta L equals alpha L naught delta T. You have delta V equals beta V naught delta T. And you have P1 V1 over T1 equals P2 V2 over T2. These three equations should get you rolling on your assignment tomorrow. Make sure you ask any questions if you have them in class. Bye for now.